Yeah, good morning. So now we are going to continue the session. Recap before starting today's session. We will just recap. So we have started a regularization, and we have covered a lot of topics. Regularization in deep learning, particularly basic concepts which are essential for regularization. Why we are preferring regularization and parameter norms. So you know that we are applying some penalties. So how we are applying these penalties, parameter norm penalties and norm penalties as a constrained and under constrained problems. And also we have discussed data augmentation. So this is also one of the regularization technique, noise robustness and semi-supervised learning. And also we have covered multitasking, early stopping, multitasking, early stopping, sparse representation. So these topics we have already covered. So last topic which we discussed in the last class is bagging and other ensemble methods. So these other ensemble methods are used for regularization. So before starting this dropout method technology, regularization technique, so we would like to discuss bagging and ensemble model revision. So because this is one of the technique which is interconnected with a dropout. Okay, so the dropout we are going to continue now. Yeah, this is a bagging technique. So already we discussed in the last class, like bagging technique. So other ensemble methods also we are using. So what is other ensemble method? It is nothing but a boosting method. So bagging method is used like initially we are dividing our original data set. Initially, we are dividing our original data set into the several number of individual data sets. So here we are following individual IID model, individual identical data set description. So using this IID model, so you know that this IID, PCA, or several techniques, fundamental techniques, we already covered in second unit. You just remember how we are using this IID technique. So here we are dividing this data set into individual sets. Say for example, we have k number of data sets. The same we are using in dropout. That's why I'm revising. Okay, within 2 minutes I will complete this and I will go with the dropout method because it is already covered. So here you just see we have a data set which is having like a 9, 6, 8. Now our prediction is we need to identify by whatever the input we are giving to the model. Say for example, I am giving input like 9. So based on this input, it has to predict this input value is mapped with the any one of the data set. Then it predicts the output as a 9. Okay. So in this process, we are dividing our data set 9, 6, 8 in this example. So we are dividing data set into several individual data elements, and then we are applying for each and every individual data element. We are using a model, separate model. So for dataset 1, we are using one model. For dataset 2, we are going to design one model. Here, designing a model is nothing but an algorithm. So these models are independent. Okay, so these models are independent, but this is dataset 2, this is 3. Like we are dividing our original dataset into several individual datasets. So all these data sets are applied with individual methods, logic or algorithm, individual models. So we are developing individual models. So this division, we can say it is a bagging mechanism. Okay. So after doing this individual model development, we are taking the aggregation of these models again. We are collecting these models outcomes and we are doing aggregation. So this is nothing but aggregation. So bagging is, you know that bootstrap aggregation. Initially, we are doing bootstrapping, that is bagging technique. Bootstrapping we are doing, that is dividing the model. Dividing the data set and designing the model for each and every individual data set. This is model 1. That means algorithm 1. This is model 2, algorithm 2. This is model 3, algorithm 3. So like we are developing individual models to generate the output. So after generating the output from the each and every model, we are using aggregation mechanism. Aggregation, simply you just remember, it is a doing average or taking majority vote. Okay, so we are applying these, and then we are finally we are predicting actual output. Okay, so in the process we are doing like a bootstrapping. The model is considered by averaging, aggregating the individual methods. So like this. One second. So these data sets, after this is one model, we can say 868 is considered. This is another model, 998 is considered. So after that, for the given input value, say for example, we are giving input as 8. How we are going to consider this means, from this model, it gets the output like upper side of the 8. See for example, for this input, it is considered this model generated output like this. So from this model, we got output like upper part of the 8. So from this model, in this example, we consider only 2 models. So from this model, so it is generated bottom side of 8. So like this, bottom side of 8. So what we are doing in bagging, we are bagging all these things as a single unit. That means we are taking aggregation of average of the 2 models. So average of these 2 models is that means it is nothing but aggregation. It combines these two as a single one because it is an ensemble model. It combines 2 models output as a single output, and it predicts the output like a 8. Whatever the input is provided, that input is 8. So similarly, when we are giving a particular input like 9, maybe it predicts like this, like this. So model 1 predicts like this, model 2 predicts like this. So we are connecting these two. It looks like a 9. So it looks like a 9, like this. It looks like a 9. That is the thing here I'm going to convey is, when we are using the model bagging technique, bagging regularization technique or optimization technique, it uses ensemble mechanism. This is one of the ensemble mechanism. Using this ensemble mechanism, initially we are dividing our data set into several individual data sets using IID technique. So these data sets are applied individual, that means independent models. So this model is independent, this model is independent, this model is also independent, like n number of models are applied on data set independently. After that, every model it produces output. This output will be aggregated. That means we are considering the model average. Then we are taking as a considering as a ensemble model. That output will be predicted as an accurate output. So okay, so like this we are implementing this bagging mechanism. This is our last concept which we discussed in the last Monday. Okay, so now we are going to implement boosting. Boosting is also one of the technique, but boosting we are not using in our dropout method. So already we have covered boosting is strong learning mechanism compared with the bagging. Bagging is a weaker learning mechanism because it is independently develops the model and doing the aggregation. But here the boosting point, a model is generated. This model gives the output. Based on the output, we are going to consider the error value. So, and we are refining the model, and again we are creating the model. Then this model also gives output. Then we'll consider error value, and we are refining the error. That means optimizing the error. So, like this optimization we are implementing. So, it is a boosting mechanism. This model is model 1 is having maximum error. Model 2 is reduce the error. By boosting this model 1, we are generating model 2. Boosting this model, we are generating model 3 outcome. Like this, it is interconnected. It depends on model by model. It's not like an independent model. This is boosting. Anyway, it is not used in our dropout. In dropout mechanism, so we are using only bagging mechanism. Okay, that's why I'm repeated today. So anyway, so we are going to discuss about a dropout. What is a dropout and what is the importance of dropout? So this dropout is one of the ensemble model. Okay, it is implementing like a boosting mechanism. We can be considered interconnected with this dropout mechanism. So this provides computationally expensive. That means when we are designing a model computation is complex, that is expensive. But the model construction is expensive, even though it is having one of the powerful regularization method. That means it is generate minimum generalization error with compared with the other models. So you know that minimum generalization error. So our overall target is we are reducing this error, generalization error. So this generalization error we are also called as training error, testing error. Okay, this is you have to correlate with overfitting underfitting problem. Okay, you just remember all the times you have to remember this diagram, graphical representation. This is generalization error, this is training error. Okay, this is capacity, that means best optimization point we can consider as a capacity, optimal capacity. This is generalization error. So this is underfitting, this is overfitting. So you have to remember this diagram, all the cases. So when we are discussing the model, our intensity is we are going to regularize the model. So regularization means already we have discussed in the starting of the unit. We need to find this best point. Okay, so because this is the best point, optimization point, which regularize our model. So otherwise, a model will be underfitted model or overfitted model. So to overcome these underfitting and overfitting problems, we are going to do optimization, that is a regularization. So using several techniques, one of the technique is a dropout technique. Here we are discussing. Earlier, bagging boosting is also discussed. Okay, so what we are doing here, the dropout mechanism, which can be implemented, but it is computationally very expensive. That is, it is very complex computation task will be involved, but it is gives minimum generalization error while generating the model prediction. It gives optimum value. It regularizes our model. So comparing with other model like a bagging model, boosting model, some PCA model and other models. So this gives more accurate result. So it in bagging, what we are doing in bagging, that's why we are discussing today morning. What we are doing in bagging, it involves training multiple models and evaluating multiple models on each test sample. That means individual data set is considered. For that data set, test sample or training data, testing data. So we are considered test sample. With this test sample, it performs individual operation. Okay, so this model is large network. That means when we consider a large network, applying this bagging mechanism is difficult. So impractical means it is difficult. So to avoid this difficulty, so we are using dropout mechanism. So this dropout mechanism is implemented by removing non-output units. Say for example, we are constructing a model by considering the units like input unit. Okay, so input units are there in input layer. Okay, in this example, we'll consider one input unit from one x1, another unit is x2. This is there in input layer of the model, and we are using hidden layer, one hidden layer. Say for example, this is hidden layer, one hidden layer we are using. In this hidden layer, say for example, we have two units, hidden unit 1, hidden unit 2, and so on. We can use n number of hidden layers. Okay, that's based on the model, and we are predicting the output as one unit. Okay, we are predicting one output unit Y. So I'm not using weight values and all. It is a brief idea. So like this, when we are constructing the model, when we are using this dropout, so this dropout technique implements, it is not considered or it removes non-output units from the network. Okay, non-output units. That means this is one unit, this is one unit, this is one unit, this is other unit. So while constructing the model like this, whatever the layer, whatever the unit is not generating the output, so we are removing that non-output units from the network. That means we are dropping out the units. So which unit is not generated a particular output. So what is the meaning of not generated output? This non-generated output means it is considered like a negative values. Whenever the model is generating negative value, so we can say that value is not required for the computations. That means to reducing this error, generalization error. So we are not considering this. So we would like to remove that particular component or a unit. So then our model will give more accurate, that means reduced error while predicting the output. So that's why we are removing such output errors. That means non-output generate. That means the unit which is not generated the output, that output unit will be removed from the output layer. So you just consider this example here. So we are having a base network. This is a base network, basic network. So it is having input layer, which is having two units. It is having one hidden layer with two units and one output layer which is having only one unit. So while designing this model, dropout mechanism, first you need to identify what are the subnetworks are formed with this network. So ensembles of subnetwork, that means combination of the subnetworks. This is one subnetwork. This is another subnetwork. I will explain this. Here we have like 1, 2, 3, 4, 1, 2, 3, 4, 8, 4 by 4, that is 16. Okay, we have 16 subnetworks. All these subnetworks are ensembled. Ensemble means a combination. We can take collective or combination of the networks. So this is input unit and it is not generated the output. There is no path from input to output. And this is one subnetwork. It is having hidden layer, hidden unit, and it is connected with output, but it is not connected with the input. This is another sublayer like a hidden unit. So this is having only output without it. Like the base model can be divided into submodels, sublayers, like only having input value X or input value with the hidden value. This is input value with hidden value. So another input unit with the other hidden value and output value. So only input value, only output value, that is only output value without having the connection. So we can construct a model like this. We can divide our base model as a n number of ensemble. That means subnetworks. There is a possibility. This is the final overall possibility of the model. So overall, what we are applying here, so where we are applying dropout, earlier diagram is not having any dropout. Earlier diagram is represented how we are dividing subnetworks from the main base network. Here, you just consider the subnetworks with the values. Okay. So we are going to consider one element. Okay, mu. So what is the meaning of this mu here? So it is an input unit. Okay, mu is a random parameter. Okay, so we are applying a random parameter to each and every input unit, as well as hidden unit, input unit or hidden unit. Okay, so this mu is a random parameter we are considering. This random parameter is applied for the input unit or a hidden unit. Say for example, here we are using mu parameter which multiplies with the input value. Okay, this value will be considered as one of the input, random input, by using random parameter. So, okay, this is connected here as an input unit. That means random parameter is considered as an input parameter. This is related to input unit 1. And similarly, we are using input unit 2 random parameter, input unit 2 random parameter. These two are added in the input layer. Okay, these two are added in the input layer. This is, and comes into the hidden layer. If we are, while constructing the model to reduce the generalization error, so we are applying all these things. So sometimes we can apply here as an input unit, or else we are not considering here. We can apply in the hidden layers. Okay, random parameter for this hidden layer is added with the random value. Hidden layer 1 having hidden layer first unit having a random parameter, it is added. Hidden layer second unit having random parameter, this is added. Okay, so by adding these two, we can generate the model. Okay, by applying hidden layer 2, so we can generate a particular output. That means we are adding one random parameter, say mu. This parameter is applied either input unit or the output unit. Okay, so the output will be predicted. This will be a probability of the value. So output of the output, that is y, based on the constraint is x. Okay, so we would like to consider average value of this input value which generates a particular output. Through this input, we are generating output. This is a conditional probability we are using. So summation of all these conditional probabilities with n number of units. With n number of units. That means we would like to consider average value, that is mean probability of input values and all input units from the input layer to output layer. We are making as a summation, and then we are dividing with the total number of units. So we are going to generate this. This is a probability we'll consider. Similarly, when we are using parameter, random parameter, so where we are going to add parameter value like probability of mu into probability of y given mu comma x. That means it is considering input value mu and x as a parameters, like this layer we are considering. So input value and random parameter value which generates the output based on the condition. Okay, so with this we are using random parameter here. Earlier without random parameter, here this is using random parameter mu. Okay, so random parameter mu is multiplied with input unit, or it will be multiplied with hidden units. So this is also generated. Okay, so like this we can apply the probability to generate the output in this whole process. So what is the probability will be considered in a dropout layer is for the hidden layers, the probability it is going to be considered like a 0.5 as a hidden layer probability, and the input layer probability is 0.8. So by default, it is going to be considered. This is the threshold value. That is, we can say it is a constraint. Okay, threshold value will consider like this. So based on this, we are going to apply. We are going to multiply each and every unit corresponding with the related mask. Mask means hidden layer. Okay, so like this we are doing. So in this process, we are not at all consider a particular layer. This is an actual point. So this layer is not considered. Which layer is not considered? Say for example, it is not generating the output with this combination. It is not generating the output. That means negative value will be generated. So we are going to remove this layer from the network. Okay, we are removing this layer from the network. So our network will be X1, X2, say simplicity, you forgot about this random parameter. X2, hidden layer 2, hidden layer 1, hidden layer 1. This output will be connected with hidden layer 1. And hidden layer 2 to it generate output value like this. And hidden layer 1 to also it generate output. But hidden layer 1 is not having any input because we are dropped this network because it is having negative value. So we are considering this as a 0. So 0 value into output of this x2 is also 0. So we are not consider this part. So we will consider only this part as a subnetwork of the model. Okay, we are going to consider subnetwork of the model. So like this, we have, these are all the subnetworks. Okay, how these subnetworks are formed? So these subnetworks are formed based on the dropout of the layer. Okay, here this network is, you just consider this network is formed by dropping x2 unit output. Okay, so the x2 unit output is not considered here. So we are removing this from the network so that the subnetwork will forms like this. This gives the prediction. That means this gives the output value, predicted output value. Okay, so with this predicted output value, we are comparing with the actual output and then we'll identify the error. Okay, so like this, we can consider another example, another sublayer. Say, for example, you take this one. So here we are considering two inputs. Okay, the output of the hidden layer is not considered here. Output of the hidden layer is dropped from the network. So the input which is passed to this only one hidden layer unit, only one unit, another unit is dropped. So with this, we are predicting the output. So this predicted output is compared with the actual output. So likewise, we are applying, we have a possibility of 16 subnetworks from this network. So all these 16 subnetworks are ensemble. That means interconnected, more than one combination. So like this, we are using this dropout mechanism. Overall intensity is when we are dropping a particular layer from the network, that means a model. So that gives minimum error because there is no need of doing computations. Okay, no need of doing computations. So we are reducing the computations. So that's why we are generating more optimum output compared with other models. Okay, so like this is one of the major thing we are doing here, and then comes into the another training model, that is adversarial training model. So what indicating this adversarial training model? So this is one of the model which is developed based on the human mind. Okay, human perception. Okay, so it is just to see here. In many cases, neural networks have begun with reach human performance when we are evaluating IID test set. Okay, so what is the overall motivation using this adversarial training model is? It is motivated by human evaluation system. Okay, so we are trying to develop a model that is performs as how human being is performing. In this performance point of view, we are going to design, we are going to train our model by evaluating IID set. Again, IID set. It is individual, independent, identical data. IID. So using that, we are going to predict output. For that, we are designing the model. So how we are designing this model, you just see this diagram. So with this diagram, you can easily understand. So we would like to predict the output of this particular image in image processing. So we would like to predict this image. So in this advisor model, what we are doing is, so we are going to consider this weight value. Okay, this weight value. This is input value. This is input image. the weight value, so which can be considered like a sine weight value. Using sine function, we are going to we are adding some extra information which is similar to sine value. Okay, so here we are considering delta x of j, x theta xy. This is parameterized, what we call parameterized input and output value, so which is generated using parameter norm penalty. Okay, parameter norm penalty. Here j is a function, theta is a parameter. So here we are applying L1 regularization to reduce the weight value, weight decay. Okay, so this value is applied. That means norm penalty value is applied with the sine function. Okay, so this is activation sine function. So using this activation function, so what is the input of this activation function? The input of this activation function is defined from the parameter norm penalty. By applying parameter norm penalty, this is the first topic we discussed in this study. Okay, that means this parameter is applied to the sine value, sine function. Okay, so here we are considering this as the input value. Okay, input value. Say for example, so 8.2% of the weight value will be considered in this example. So this is directly derived from the Goodfellow, Ian Goodfellow. He is the author of our deep learning, machine learning. Okay, what we are following a textbook. So this is written by Ian Goodfellow. So we are considering. He did some experiment using adversarial network. In that experiment, he is added this value. It is equal to sine value. So this will be implemented using the model is called pre-training model, transfer learning model. We can say transfer learning model. This is one of the simplest and accurate image processing model. Google Net, we can say Google Net. We can say it is Google Net, not Google Net, Google Net. We can say. So, but pronunciation will say Google Net. Using this Google Net, he is considered one input image in the image processing. Okay, so in this input, the output will be predicted by creating adversarial network by adding a value, input value. So this input value is parameter norm penalized input value. So using this parameter theta value, so we are taking a reduction of the theta value. That means weight value reduced error value that as input to the sine function. Okay, so this will be added to this input image. Okay, so then it predicts the output, image output accurately. Okay, so direct input, when we consider direct input, the prediction is 57.57. But by adding this noise value, that means extra input, 8.7% with a parameter. Okay, so we are going to consider this is learning rate parameter. So what is learning rate parameter? Learning rate parameter always take in between 1 to 0. Here he considered 0.07 with this value. So then the model prediction will be high confidence. The model prediction will be 99.3% is accurate. So if we want to do these modifications or changing this parameter value, so you have to do this by reproduce this output with the permission of Ian Goodfellow because he is having copyright. So this is the one mechanism. That means here you just simply see here it is nothing. This image doesn't have anything. This is only a blank image. We are adding this blank image to our actual image, even though it gives more predicted output than the normal image. Because why it gives more accurate output? Because in the image processing, every feature is important. In the image processing, every feature is important. color. Okay, so here uh, we can consider all these features like in terms of it retrieves the data from the pixels, pixel by pixel. This is also we discussed in the norm-penalty regularization. Okay, so that's why we are using norm-penalty as a sign. So we are considering only a particular picture. Okay, so only a particular picture. So these pictures will be considered, and we are ensembling all the pictures as a single unit. Then we are predicting the output. So this is one of the ensemble mechanism. So these pixel extraction of these pixels, we are considering background images also. We are considering background images. While extracting a feature like this, nose point, eye point, this one. So every pixel information is gathered. While gathering these information, each and every pixel data is important. That means color is also be considered. Color is also one of the key feature in this image processing. Okay, to give more accuracy, so we are adding some extra information like this. Even though by adding this, our pixel density will be increased. The feature map should be, the feature is feature map, that is output. Feature map is accurate with this particular feature in color of this image. So this is one of the advisory technique. So this is inspired by the human mind. Okay, so that will be considered here to train our model. So this is one of the technique we are using in our regularization of a training model. Okay, so then comes into the optimization for training and deep learning model. So this optimization technique. So till now we have discussed so many regularization techniques. That means which controls the model. The optimization is also one of the controlling technique. Model is optimized or model is controlled. Then we can say that model is produce the more relevant or more nearest value of the actual value. So for that we have several techniques we are using. Okay. So those techniques are simply we can say PCA, principal component analysis. Okay, under ICA, we are using this ICA. It is identical component analysis IDA and ensemble learning. So till now we have discussed regularization techniques like bagging, boosting, uh, multitasking, dropout, which follows ensemble learning mechanism. Okay, so in our optimization technique, we will see these two other algorithms along with the basic algorithm. Okay, we would like to learn these optimization algorithms. Okay, this we will learn in the next class. Okay, these two are very important optimization algorithm. These two are optimization algorithms as well as ensemble algorithms. Okay, so that we'll see in the next class. This is important. With this, I'm going to finish a third unit. Probably today I will take another class with permission of other faculty. Otherwise, I will take this class on Monday. I will finish this on Monday. So, any student is having any doubt, please raise your doubts. You can contact me as usual in WhatsApp also, raise your queries. If you are feel any difficulty, text me in personal. I will explain those concepts if you have any. Okay. So I would like to give you information like 1 second. Video sessions, I mean recorded sessions are there. I will share you recorded sessions After, today I will share you third unit complete material and also video recorded sessions also. So you can follow these recorded sessions if you want.